I'm thrilled to welcome you all today to our webinar on HepaRG, the unique hepatic cell model. I'm Pamela Alazzi from BioPredict, and I'm delighted to be your host and guide throughout this webinar, one among others organized by BioPredict to support liver in vitro research. Thank you for each and every one of you for joining us today, and special thanks to our esteemed partners who will be animating the 3 sessions of this webinar. Before we get it started, please note that this webinar is recorded. A link of the recording will be sent to you a few days after this webinar. If you've got questions, ideas, or would like to engage in discussions with our speakers, feel free to write your messages in the Q&A box. We will have a short Q&A session after each presentation. For the first part about liver fibrosis, let me welcome Dr. Leo van Grunsven, who will give an overview of the progress in developing complex 3D liver cultures with a strong focus on HepaRG and human stellate cells co-cultures. Leo has got a PhD in neurocell biology from École Normale Supérieure de Lyon and a postdoc training at US and Belgium focused on neuronal differentiation. Since 2009, he heads the liver cell biology research group at the VUB Belgium. His research group studies molecular mechanisms involved in liver homeostasis, fibrosis, and regeneration, with a special focus on hepatic stellate cells. His group was the first to identify autophagy, age, and hyposignaling as key mechanisms involved in hepatic stellate cell activation during liver fibrogenesis. His team pioneered in the establishment of an hepatocyte injury-dependent in vitro liver fibrosis model by using spheroid cultures of HepaRG and hepatic stellate cells. The research efforts of his lab now also include induced pluripotent stem cell-derived hepatocytes and the human stellate cells as a cellular source for these spheroid cultures. Leo, it's yours.
Thank you, Pamela, for the introduction and for inviting me to be part of this webinar. Let's see whether I get this straight. Okay. Hello, everyone. So as Pamela already introduced, I'm going to talk about in vitro liver fibrosis modeling and the use of HepaRG cells in this system. Just a brief introduction about our lab. So we're focused on we're located at a medical campus in Jette, which is close to Brussels. Here in the, wait, I get the pointer. Here in the background, you see Brussels, and here's our lab, and we're close to the university hospital. The focus is really on hepatic stellate cells. So I'm maybe a bit different from the other 2 speakers of today who have more a strong focus on hepatocytes or on HepaRGs. We want to know how come hepatic stellate cells activate and are the main source of collagen during fibrosis. So as a small introduction, everybody knows chronic liver disease is a big health problem. Main causes of chronic liver disease are hepatitis infections, steatotic liver disease, alcohol, but also drug intake. And it takes many years to get a fibrotic liver, which you're usually not very aware of. And then it is followed, a small percentage of people with a fibrotic liver will have a cirrhotic liver in the end. And there's so far no real medication available to prevent fibrosis formation or in the end cirrhosis. Which means that currently roughly 150,000 people die every year in Europe because of chronic liver disease. So why are there no efficient antifibrotic therapies? Well, it's a very complex disease. Many cell types are involved in the liver, but also there's gut liver axis, fat liver axis that is very important. And it's very difficult to study this, especially in vitro, because the models that we have currently do not present very well the very complex liver microenvironment that we have to study. Although big progress has been made recently, and you will see a talk later on about this. Moreover, there's a species variability. So if drugs are found that do very well in mouse or rat, in the end, when they go to clinical trials, they show toxicity in the liver, or they just do not work in humans. So we need in vitro models, mainly because of this species variability as well. So we need very good human models to model these chronic liver diseases. And also we need in vitro models to reduce the number of animals used for experiments. I pulled out some data from 2019 from the Allures database, which reports on animal use in Europe. And these are the numbers of 2019, 4.6 million rodents, mice, and rat are used, of which roughly 650 to 700,000 are used for toxicology and gastrointestinal studies. So it would be a good thing to reduce this, and Europe also asked us to reduce this. So what would we like to have in vitro? Well, the scientific dream of every liver biologist working with in vitro models is that we could recapitulate a liver lobule in which the blood would flow from the portal vein to the central vein, and that we could create a system where we have functional hepatocytes, but also that the blood or the medium is filtered by LSEC through healthy using healthy fenestrae. The hepatocyte would, of course, be detoxifying, so we could test drugs detoxification. But we would also like to see, and this is the focus of our lab, is that the stellate cells would behave as they would do in the liver. And what is this? Well, if you have a regular liver, these stellate cells are located here in between the liver sinusoidal endothelial cells and hepatocytes. They're in the so-called space of this, where they're very quiescent. They have a very low ATP production, and they produce some collagens, and they maintain the stability of the liver. They store also large amounts of vitamin A in lipid droplets. Now, if you have an unhealthy lifestyle or you're infected by hepatitis viruses, you damage these hepatocytes. And this damaged hepatocytes will lead to activation of Kupffer cells and recruitment of monocytes to the liver. So an inflammatory response will take place, which will lead to activated hepatic stellate cells, which then will produce high amounts of extracellular matrix, which will be deposited in the sinusoidal space of Disse. Now, many years ago, already in the 80s or 70s, we found systems in vivo in the mouse that we can kind of recapitulate this, which means that we can inject a mouse with carbon tetrachloride, and this will lead to hepatocyte damage and also inflammation and hepatic stellate cell activation, as you can see here, is illustrated by cross-linked collagen and SMA and collagen positivity. So we can do this already for many decades, but what the mechanism of this stellate cell activation is in vivo was very difficult to do, especially in the 70s and the 80s, because mouse models were not very well established yet. So in the early 80s, people discovered how they could isolate these quiescent stellate cells from healthy livers. If they put them in culture, they look like this, very small cells with these yellow lipid droplets inside of them. And over time, these stellate cells will activate, become very big myofibroblasts here, this one cell here, big myofibroblasts, which also express large amounts of alpha-smooth muscle actin and collagen, like they would do in an activated stellate cell in a fibrotic liver. So this was a very good system, and people have really discovered a lot of mechanism of how stellate cells could activate. Now, how do we do this normally? We isolate primary stellate cells from a mouse. We can isolate hepatocytes from this mouse as well. We can fax these stellate cells based on vitamin A in these lipid droplets. And these are very pure cells with very little contamination. You can also isolate these stellate cells by doing a nicodens gradient, but these are less pure. We use the same technique later on. I talk about primary human stellate cells. We do use the same technique to isolate human cells from livers, but of course, we cannot perfuse an entire liver. We get pieces of liver from resections, for instance. So what happens if you put these stellate cells in vitro? Since these cells activate really quickly, here you see freshly sorted stellate cells that are plated, and it's a time frame of 3 hours, 12 hours, 24, and 96 hours. And you see that the first 12 hours to 24 hours, not much happens to these cells. They have a lot of lipid droplets. They're a bit stretched, but only after 4 days, up to 7 days, then they become really, they get a really myofibroblastic phenotype. And you also see that these lipid droplets, they disappear. In other studies, we've seen that these lipid droplets disappear because of autophagy, because they need the energy to activate. A while back, we looked at how these cells would activate, and you can see that although you don't see any phenotypic change up in 24 hours, you see a lot of things happening at the transcriptome level. So this is RNA-seq analysis of isolated stellate cells. And already after 6 hours, very important transcription factors, but also targets of cell adhesion molecules are quickly upregulated, like KLF6 and anchor D1, while only after 4 days, typical myofibroblast markers like LOX go up. Now, we looked at this very early changes in stellate cell activation transcription program, which we call the initiatory program after 6 and 12 hours, is also up in 4-week CCL4 isolated stellate cells, but even in stellate cells isolated from cirrhotic liver. So these very early steps during stellate cell activation, which we see in vitro already happening after 6 or 12 hours, this happens in an in vivo mouse liver and in vitro and in vivo human liver, even during cirrhosis. So what happens during these first steps is that a hippo signaling protein, which is called YAP, is in the cytoplasm when cells are isolated. These are cytospin stellate cells. And when you look after 10 hours, this protein is already in the nucleus. And it stays in the nucleus until the end of differentiation. And we looked in mice, but also in human. And this is also the case. If you look in activated stellate cells in a mouse model of fibrosis, you also see that the smooth muscle actin, so the myofibroblasts that cause fibrosis, also have YAP in the nucleus, at least 50% of these cells. So why am I telling you all this? This is how we got into the field of co-cultures and the use of HepaRGs, because we found out that if you plate cells in 2D, they will activate because the rough surface activates YAP, or the hippo signaling is turned off, and the stellate cells activate. However, if you put these cells, the same cells, freshly isolated, you put them in spheroids, hippo signaling is on, and YAP goes in the cytoplasm, and stellate cells remain quiescent. And this is briefly illustrated here. In black, you see the upregulation of alpha smooth muscle actin, or ACTA2. Over time, in 2D, it goes up 400 to 500, 600 times, while in 3D, it still goes up to like 10-fold, but it's much less than compared to 2D. So if we really want to look, if we want to study stellate cell activation, and not because they touch a rough surface, a very tough surface, but we want to induce the stellate cell activation, we thought, well, it would be good to culture these cells in a spheroid. Here's just a small, some proof that actually YAP signaling is important in this, because after 10 hours, you see YAP downstream targets, CTGF and anchored go up, while this does not happen in 3D. So is 3D the solution to not have just a culture-induced activation, but actually to have a better activation model would be to culture them in 3D. Well, of course, if you only use mouse stellate cells or human stellate cells, you still cannot mimic the damaged hepatocyte model, because in vivo, fibrosis does not just happen because of that. On its own, you need a damaged hepatocyte to induce this stellate cell activation. So many years back, we started with differentiated HepaRGs from BioPredict, even before WePredict existed. And we used these differentiated HepaRGs. They come in frozen vials. We thaw them, and we combined them with primary human hepatic stellate cells that were isolated from donor tissue from the hospital. We passaged these primary stellate cells for a couple of passages, and then we put them together with the HepaRGs. They form balls of roughly 2,000 cells, well, roughly 200 micrometers, because we put 2,000 cells in, and the ratio is 2 stellate cells towards 1 HepaRG. If you open these up, you see that the stellate cells are in the center of the spheroid, and the HepaRGs are more surrounding the stellate cells. And you can see here a staining of CYP3A4 for HepaRGs or hepatocytes, and PDGF receptor for the stellate cells. What we also notice is that if we put the activated stellate cells together with these HepaRGs, they became more quiescent. So they lost a bit of their collagen and smooth muscle actin, which indicates that they become more quiescent. So then we thought, well, if we just damage the hepatocyte, we can maybe turn these quiescent stellate cells into an activated phenotype where they again produce collagen and log cells. So this was our very minimalistic liver fibrosis model. And we tested this by exposing the cells to APAP. And as you all know, it's a very well-known toxicant for hepatocytes, and also relevant for human exposure at least. So if we did this when we had the cultures for like 20 days in culture as spheroids, we can see here that if we use increasing amount of APAP, there's ruffling of the spheroids. And we see that the hepatocytes die at the rim of the spheroid, and there's collagen deposition. I'm sorry for these stainings. They are not the best, but they're from the original 2016 paper. So, so since you can also look back in this paper, to make a long story short, we could show that in these HepaRG stellate cells, primary stellate cell spheroids, we could show that methotrexate could also induce fibrosis, allyl alcohol could induce fibrosis, and also APAP could induce fibrosis. Meaning that if we added this in either acute or a chronic exposure, we could induce HepaRG cell death, or at least damage, and stellate cell activation by showing fibrosis, collagen deposition, or extracellular matrix production. When we submitted this paper, in the end, they asked, well, you know, APAP is not really relevant because nobody has fibrosis because they take paracetamol. We gave it to mice for 4 weeks at low dose, and we actually did see that there is fibrosis in these mice as well. So we can use indeed the model to predict fibrosis development. So what did we do since the first paper? We wanted to shift away from these primary human hepatic stellate cells because you cannot passage them forever. They're a variable source. It's not very stable. Each time you have a new batch, they differ, and I'll come back to that later. So together with the lab of Catherine Verfeuilly in Leuven and Pau Sanchez-Bru in Barcelona, we developed a method to differentiate pluripotent stem cells to pluripotent stem cell derived stellate cell-like cells. Now, it's a 12-day differentiation protocol, and at the end, these induced pluripotent stem cell or human embryonic stem cell derived cells have look a lot like the primary human stellate cells that we isolate from the liver. We did some bulk sec on these differentiations, and we can see that IPS, once they differentiate, once they're pushed towards differentiation towards the primary human hepatic stellate cells, which are here indicated in purple, the final passaged IPS-derived stellate cells take on a transcriptomic profile that looks a lot like the primary human stellate cells. And we did a lot of characterization, and you can see this in these two papers. They express different stellate cell markers. You can induce them directly, so activating stellate cells through giving them TGF-beta or a PGGF ligand or even LPS. We can induce a profibrotic stimulus in these stellate cells without just in 2D. And we can also store vitamin A in the lipid droplets. Now, do they also become less activated when we put them in 3D? We tested this. So this is how a IPS stellate cell HepaRG culture looks like, or a primary human hepatic stellate cell HepaRG. So this is CYP3A4 for the HepaRGs, and the stellate cells are in the center of this cultures. HepaRGs alone, of course, do not have any PTGF receptor positivity. If you now look at two markers of stellate cell activation, LOXL2 or collagen 1A1, you can see that in both spheroids. So here in grayish, you see primary human hepatic stellate cells with HepaRG, and in green, IPS-derived stellate cells. They have high levels of LOXL2 to start off with, but after 7 and 14 days, there's a big drop of 5 to 7 CT values, which means 32 to 64 fold down regulation of LOXL2, but also of collagen. Here, IPS-derived cells, you see 10 CT values, so over 100-fold down regulation of these activated stellate cell markers. Same thing is for collagen 3 and ACTA2, although less prominent. So both primary stellate cells and IPS-derived stellate cells, when we put them together with HepaRGs, they become less quiescent, less activated, so more quiescent, and we can induce them. And we can induce them again, for instance, with APAP. So here you see IPS stellate cell with HepaRG in a control culture. There's very little serous red staining, and serous red stains the cross-linked collagen. And here you have a regular collagen staining. There is, of course, collagen because stellate cells produce collagen a bit. But if you expose them to APAP, the collagen production is much higher, and you also have cross-linked collagen, serous red staining, reminiscent of serous red stain that you see in a fibrotic liver. So we can also look at RNA, and we see that in both conditions, when we treat with APAP, and the dotted line is the control condition, if you treat with APAP, these activation markers, LOXL2 and collagen, are upregulated in both primary stellate cells and IPS-derived stellate cells cultured with HepaRGs. So we have a hepatocyte damage-induced fibrosis using HepaRG as a hepatocyte source and adding either primary human hepatic stellate cells, human embryonic stem cell-derived stellate cells, or IPS-derived stellate cells. We can also take the medium from these spheroid cultures, and we can look at collagen in the medium, and we can see in both cases that APAP induces collagen secretion from these spheroids. So everybody always then asks me, well, why take HepaRGs and why primary human hepatic stellate cells? We can just use LX2s and HepG2s, and yes, you can. But for instance, in a culture here, for instance, HepaRG alone over 21 days, these spheroids do not increase much in size. Stellate cells, when you put them alone in culture, they become a tiny bit activated. So the spheroids start to contract a bit, so they become actually smaller in size. And HepaRG stellate cell cultures also more or less stay the same over 21-day culture. And as we've seen before, they do not activate. If you take HepG2s, LX2s, you take the same amount of cells. Of course, these cells are cancerous. They keep on dividing. So HepG2s, the 21-day culture, many cells are still dividing, as here shown by an EDU. They also increase in size a lot. So this is already going to the 500 micron level. And what's even less interesting, if you want to look at stellate cell activation, and we look here at collagen 3A1, for instance, in both LX2 only cultures or HepG2 LX2 cultures, there's a high increase of collagen over time, and these are delta CT values. So 10 delta CT values is more than 100-fold upregulation over time. Same for OLOXO2, although less. If you have HepG2s, of course, they don't express much, but if you have HepG2s with LX2s, they're upregulated like 6 or 7 delta CT values. So if you want to look at stellate cell activation, I would not use regular cell lines. And now my computer is blocked. Ah, no, it's not. Okay, so what I've shown so far. Okay, what I've shown so far is that if we use primary human hepatic stellate cells together with HepaRGs, they become more quiescent. But we're stuck to iPS-derived stellate cells. We have to differentiate them all the time. And the primary human hepatic stellate cells, we have to isolate. So that was not, if we want to expand and use different sources, we would like to use all other sources as well. So we wanted first to replace primary human hepatic stellate cells that we isolate ourselves, because it takes a lot of effort to do this and to characterize them. We wanted to use a commercially available one. So we got our hands on some biopredict lines, BP11 to BP17, and these were from different donors. And we wanted to know, well, do all different stellate cells isolated from different donors, do they behave the same? So if you put them together with HepaRGs, we can already see that in, for instance, BP17 stellate cells, there's very little PDGF receptor beta positivity. You could think, well, maybe it's because you didn't put enough cells, but PDGF receptor positivity is also a sign of activation. So stellate cells do have PDGF receptor beta, but if they're activated, they express more. So this could be one of the two. BP16, for instance, at day 15, it has many PDGF receptor beta positive cells. So to test whether these four conditions, these four stellate cells would activate in the same way when we expose them to different compounds, we exposed the HepaRG cultures alone, or the HepaRGs with BP16, which had a lot of stellate cells or a lot of PDGF receptor positive cells, or HepaRGs with BP17, which seem to have quiescent or at least less stellate cells, to APAP or TEA. And you see that APAP somehow induces a tiny bit of collagen staining here, and there's a bit of collagen staining here in TEA, but not that much. If we now use the BP16 stellate cells together with HepaRGs, we already see a lot of collagen in the control, and there is some induction, although it's not very significant if we expose these spheroids to APAP or to TA. However, BP17 is clearly our winner, because in a control condition, there's very few collagen production, and if we expose to APAP or TA, we have a high increase of collagen production in these spheroids. So it means that, yes, it's very good to have, you can get primary human hepatic stellate cells from different vendors, but you really have to check which stellate cells you put together with HepaRG. Now, what about iPS-derived lines? So are all iPS lines similar? So we focused on two iPS lines, which I call here iPS line number 1 and iPS line number 2. These are completely different lines that you can buy. And you can see here that if you put HepaRG together with iPS line 1 as iPS line derived stellate cells, you see very little picoserous staining, while here you see a clear ring of serous red when you use iPS derived stellate cells number 2. Primary human hepatic stellate cells with HepaRG, as we've shown before, do not show anything. If you put them together with primary human hepatocytes, it shows that the similar things happen. Again, number 2 gives cross-linked collagen if you use iPS-derived stellate cells, number 2. Also showing that HepaRGs and primary human hepatocytes behave similarly in making iPS-derived stellate cells more quiescent. If you look at the abundance of PDGF receptor positivity, you see a high PDGF receptor positivity of this iPS-derived stellate cells number 2, but 1 is a lot lower, and also human hepatic stellate cells primary is also lower. So there's a strong correlation between the deposition of the cross-linked collagen and the activation status, so the amount of PDGF receptor positivity of the cells that you put in. This brings me already to the end of my talk. I hope I've given you some insight in how liver fibrosis happens and how you can model this in vitro. And I think the best way is to model it in 3D, because putting stellate cells in 2D will activate immediately. And of course, you can serum starve these cells and then push them with TGF-beta, but it's maybe not the most relevant way to study stellate cells. And I hope I also convinced you that HepaRGs, at least the differentiated ones, are a very good basis to serve to co-cultures, iPS-derived, ES-derived, or primary human hepatic stellate cells together. But you have to keep in mind which hepatic stellate cells you add. And this is the same for if you use primary human hepatic stellate cells or iPS-derived stellate cells, you have to do some quality control. The questions that remain: is this the perfect in vitro model to find a cure? Well, I don't think so. We need to improve co-culture conditions, that we can culture them even longer, make them even more stable over time. We have to create more structure, because as you've seen here, and which will actually be addressed by the next speaker, by Rennert, is we don't have any structure. This is a ball of cells, which stellate cells are in the middle, and the hepatocytes are surrounding these stellate cells, but there's no vasculature, there's no flow really inside of the spheroids. We could probably optimize it much better by integrating flow in there. But for this, we need to incorporate more cell types and maybe even link it. If we want to make it disease related, we also have to link it to fat tissue, for instance. The incorporation of more cell types we have been doing, and I don't go into this, but we have been using also primary mouse, which is for us still the best model to use, but also co-cultures of 4 cell types of mouse or 4 cell types of iPS-derived hepatocytes, stellate cells, Kupffer-cytes or monocytes, and endothelial cells, put together either in spheroids as well or in gels, to have at least the complexity of the different cell types. But again, also here we lack structure. So I'm looking forward to the talk of Professor Rennert. And linked to that, we need probably better iPS-derived liver cells, even get a better handle on getting very stable iPS-derived stellate cells, that they don't differ whether you have IPS number 1, 2, or 16, because in the end, you also would like to have IPS from different donors which carry different SNPs, for instance, a SNP in PNPLA3 or HSD17, to see whether these stellate cells would behave differently in this in vitro fibrosis model. And of course, you need to adapt for high throughput screening, but again, there's another talk as well that might facilitate more high throughput, because I have to mention that this is still very low throughput and very labor intensive. But we can already use it for mechanistic studies by testing small small setup of drugs, or looking at mechanistic studies to see which signaling pathways affect fibrosis. And with that, I would like to conclude my talk. I want to thank all the members and past members. This is already a bit older image of the liver lab, our lab at the VUB, and mainly Inge for co-culture setups, but also Ayla and Mina and Laura, who did a lot of the co-cultures on iPS-derived stellate cells. And of course, I also want to thank the good collaboration with Christophe from WePredict. Thank you very much, and I'm happy to take questions.
Thank you, Leo, for this overview on fibrosis and 3D cultures and 3D co-cultures. So now we're happy to take your questions idea in the Q&A box. Okay, so Leo, it's okay to share the slides after the webinar with the participants?
Sure.
Okay, thanks. So you only have HepaRG and stellate cells in your in vitro fibrosis model. What about the other liver cell types? Did you try to add some other?
Yeah, that's a very good question. In the IPS link, we have tried to put different cell types in there because we can make iPS-derived monocytes, we can make iPS-derived endothelial cells that we can control very well. But if we like to go to primary human cells, it's much more difficult to get a good source and reproducible source of endothelial cells or LSEC or Kupffer cells. If you mix these hepatocytes with non-parenchymal fraction of donor tissue, depending on the donor, you see a lot of variation. What people now also sometimes do is they put the non-parenchymal cells in culture, they pasture them a couple of times and then put them in to get a more homogeneous culture, but it's very difficult to standardize this. And I know people at Karolinska, for instance, they use primary cells to make similar spheroids. They're very nice studies, but it's very difficult to get this really, really well optimized. And you end up testing many different batches of cells, whether they can form spheroids. Not all hepatocytes, at least in our hands, can make nice spheroids, and not all non-parenchymal cells. Also in these studies, they show that not all of them are very good at mimicking or at least maintaining hepatocyte cultures very well over a longer time. I would love to integrate other cell types, and if people have, let's say, HepaRG stable-like, but not hepatocytes, but as good, but then endothelial cells or monocytes, I would be really happy to use them.
Thank you, Leo. New idea to develop at BioPredict, maybe.
Yeah, hope so.
So did you look at the MASLD and MASH induction and fibrosis in the HepaRG human stellate spheroids, or just on toxicity?
We did some studies. I didn't include them here with HepaRGs, but we saw clear steatosis. So that's not very difficult to do. Also in 3D, people have done it in 2D. And we saw some stellate cell activation, but again, this depended a lot on the stellate cell. We've then stopped these kind of experiments, like 2-3 years ago, I guess, and we went to mouse for a while. And actually, these cultures that I show here, for instance, there we could clearly show that we can induce steatosis, that we can induce if we expose them to free fatty acids, we can have a steatosis and also fibrosis. And for instance, we could show that compounds like lanifibranor blocked fibrosis as well. So I think, yes, this is definitely possible, and we should go back to these HepaRG stellate cell cultures again to also model this. I think definitely it's a thing to do.
Okay, thanks. Leo, what about the ratio of induced hepatocytes, induced human stellate cells Kupffer cells, and endothelial cells?
Yeah, that's also it's also a good question. The ratio we started off combining HepaRGs plus stellate cells, and we did different things like a one-on-one ratio, four HepaRGs to one stellate cell, and we tested all different kind of ratios, and it turned out that as long as we put as many stellate cells as hepatocytes, or even more stellate cells than hepatocytes, actually the hepatocytes are the most happy, and that's what we wanted. We wanted to have the hepatocytes happy. It's not relevant at all. It's not mimicking at all the liver, but in our hands that worked the best. So we used 2 stellate cells and 1 HepaRG in all of our cultures, also a bit so we could more easily detect stellate cell activation and fibrosis, because if you only have, like in the liver, there's maybe only 1 on 5 stellate cells to hepatocytes. It's the amount of stellate cells is very low, so it's more difficult to detect collagen in the culture as well. If we then go to endothelial cells and monocytes, we did not play around that much with these ratios, at least not for the mouse. We keep the same ratios, 1 hepatocyte, 2 stellate cells, and then we just added Kupffer cells and endothelial cells. For the IHEP cultures, which I didn't talk about at all, we did test a lot. We did test the ratios as they are in the liver, but then spheroid formation almost does not happen. It's very difficult to study them. So we tested there 1, 1, 1, 1. It didn't work very well. So we also stuck to the same 2 hepatocyte, 2 stellate cells, 1 hepatocyte, 1 Kupffer, and 1 L6. I absolutely agree. It's not relevant. I mean, it's not relevant. It's not like in the real liver, but it's a model, and we want to keep the hepatocytes as much as happy as we can, and we want good spheroids to study and to pipette as well, because if we don't have good spheroids, we cannot pipette, at least not in our system. I think, you know, if you would put them in gels, which we're going to see later on, or if you would have bioreactors, microfluidic bioreactors where you can form layers, I think, you know, ratios can be completely different, although ratios will be difficult to determine as well in this case, I guess.
Okay.
But I have to admit, you know, we get, with every paper we submit, where we use co-cultures, we always get the same answer, the same question. You know, this ratio that you're using is really not relevant for human physiology, and then we have to agree. But it's a model, and a model can be useful and not, you know, representing really what is happening in the liver.
Yes, sure. The main objective is to mimic in a certain way what it's happened in vivo. What about increasing the number of hepatocytes within a spheroid, like 5,000 instead of 2,000?
Yeah, so like I said, we did that, and we tried more hepatocytes, but the cultures were not that happy. We did that in the beginning in like 2015, 2016. We used more HepaRGs than stellate cells, but yeah, we had the best HepaRGs functionality, which I also didn't show here, if we used more stellate cells. Now, of course, we should go back and retest this. But in our hands at that moment, using these media, and yeah, we came down to 2 to 1, which again, I agree is maybe not the best.
Okay, question from 2 questions from Rashid. I think the first one you already answered. Did you test HepaRG plus stellate plus endothelial cells and Kupffer cells in co-culture?
No, we never tested HepaRG. We only tested HepaRG plus stellate cells. We never put any other cell types on top, because we can put, of course, a Kupffer cell line or a macrophage line there, but we didn't do it. I'm sure people put, for instance, UVEX in and things like that, which you can all do. But yeah, we didn't want to put cell lines in, And non-parenchymal cells, good ones are very difficult to get. Yeah, you have to passage them, or all lines or most cells that you can get in commercially are passage cells. And then the endothelial cells are completely not relevant, and the Kupffer cells are macrophages, of course. But we've never done that. I mean, I think it's definitely worthwhile to play around with if you have good sources, stable sources of good Kupffer cells and endothelial cells. It would be very good.
Okay. Leo, did you observe biocanalicular formation within HepaRG when they are co-cultured?
Yes. It's in the original paper. We see we could see biocanalicular formation. It's not as easy to show as in a sandwich culture or the monolayer culture, because then all HepaRGs are nicely aligned and it's easier to show. But we could show biocanalicular formation. Yeah.
Okay. And do you have some tips how to induce steatosis in this model, and for how long?
In this model, I think we use different conditions, but we use palmitic and oleic, for instance. I think 200 micromolar, but I have to look back each. And within 5 days or 3 days, you will have steatosis. Sure, that would work. In the mouse cells, we could even do it for 9 days. We can keep them steatotic for a long time. It works very well, but we've never gone, for instance, beyond 2 weeks. After a while, the cells start to get damaged too much. Plus, not all the free fatty acids dissolve very well. Your media becomes kind of trouble. How do you say it? Cloudy. So at the end, it's not that nice anymore to look at. But if you, within 5 days, you should have a steatotic HepaRG, definitely.
Okay. Thank you, Leo. The last 2 questions. Did you try to perform these co-cultures with undifferentiated HepaRG cells?
Never.
Okay.
We tried, in the beginning, we were in this European consortium, and also BioPredict was in one of them. And we tried different cell types at the start, also primary, which our source was not good at that moment. And we used other cells, and then we got our hands on HepaRGs. And the moment we saw them and we put them together, they looked great. So we never went back, and we only used differentiated cells.
Okay. The last question, can you comment on the duration of the stimulus, acute versus chronic hepatocellular damage, to elicit a fibrotic response from Laura Sutterdijk?
Yeah. Hi, Laura. Of course, it's not a chronic what we do. The longest we go is we do maybe 2 weeks of culture, and it's a very thin line of damaging the hepatocytes a tiny bit and then getting stellate cell activation, or killing them too much, and the only thing you have left are stellate cells. So again, it's a model. We can show within a day or 3, we can see stellate cell activation in this model. But then again, we can also see this in mice. If we do 1 injection with CCL4 or 1 injection with APAP, you can see within 3 days stellate cell activation. They will go away after 7 days. There's no stellate cells activated anymore, but you see really quickly within 1 day already activation, and within 3 days you have collagen production by these cells if you isolate them. So the process of stellate cell activation is very quick. The really big fibrosis that you get in a chronic injury, of course, it takes much longer. So it's also very difficult to show in such a sphere to show cross-linked collagen. You have to do at least 3 days or 7 days of treatment to see cross-linked collagen coming up.
Okay. Thank you, Leo, for this talk.